Consider an experiment whose outcome is not predicted with certainty. However, although the outcome of the experiment will not be known in advance, let us suppose that the set of all possible outcomes is known. This set of all possible outcomes of the experiment is called the sample space of the experiment. Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I would like to use 10 exam questions to discuss with you the fundamentals of probability. But before going to the first exercise, let's review the concepts of sample space and events. Example number 1. If the outcome of an experiment consists in the determination of the gender of a newborn child, then the sample space will be G and B, in which the outcome G means that the child is a girl, and B that it is a boy. Example number 2. If the outcome of an experiment is the order of finish in a race among the 7 horses having post positions 1, 2, 3, 4, 5, 6, and 7, then the sample space will be all the 7 factorial permutations of 1, 2, 3, 4, 5, 6, and 7. The outcome 2, 3, 1, 6, 5, 4, 7 means, for instance, that horse 2 comes in first, then horse 3, and so on. Example 3. If the experiment consists of flipping 2 coins, then the sample space consists of the following set: heads, 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 tails, tails, heads, tails, tails. For example, the outcome will be heads, tails, if the first coin is heads and the second is tails. Example number 4. If the experiment consists of tossing 2 dice, then the sample space consists of the 36 points ij, such that I from the first die and j from the second die are equal to 1, 2, 3, 4, 5, and 6. Okay? Example number 5. If the experiment consists of measuring in hours the lifetime of a transistor, then the sample space consists of all non-negative real numbers, that is, S is equal to T, such that T is between 0 and infinity. Any subset E of the sample space is known as an event. In other words, an event is a set consisting of the possible outcomes of the experiment. If an outcome of the experiment is contained in E, then we say that E has occurred. In example 3, in which two coins are flipped, if E is heads, 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 tails, then E is the event that a head appears on the first coin. Likewise, in example 4, if E is 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1, then E is the event in which the sum of the dice equals 7. Now let's begin with the exercises. Exercise number 1. In an experiment of tossing a coin, in which we assume that a head is as likely to appear as a tail, what is the probability of a head appearing? Let's go to the solution, my friends. As heads and tails are equally likely in a balanced coin, then their occurrence have equal probability. That is, the probability of a head is equal to the probability of a tail, which is a half, or if you prefer, 50%. On the other hand, if the coin is biased, that is not perfectly balanced, and if we feel that a head is twice as likely to appear as a tail, then the probability of a head will be equal to 2/3, because we are feeling that a head is twice as likely to appear as a tail, and then the probability of a tail is equal to 1/3. When the coin is perfectly balanced, their probabilities are equal. If there is any biasing, the probabilities will be different. Exercise number 2. In an experiment of rolling a perfectly balanced die, what is the probability of obtaining an even number? That's the question, my friends. Let's go to the solution. If you roll a perfectly balanced 6-sided die, each face has an equal probability of landing face up. Since there are 3 even numbers, there are 3 even numbers in a die: 2, 4, and 6. Okay? This is the event of interest. This is not the sample space. The sample space is comprised of all possible outcomes, all possibilities. That is 1, 2, 3, 4, 5, and 6. But we do not want the entire sample space. We want this event, even number. Okay? So the probability of obtaining an even number when rolling a perfectly balanced six-sided die will be the probability of getting 2, 4, or 6. The event of interest is going to be the probability of getting 2 plus the probability of getting a 4 plus the probability of getting a 6. And the probability of getting a 2 is 1 over 6 because there is only 1, 2, and the sample space is comprised of 6 possibilities. The same for the number 4, the same for the number 6, and we sum, then we have 3 over 6, which is a half, or if you prefer, 50%. That is the probability of getting an even number is 50%, because half of the numbers are even and half of the numbers are odd. This is all for exercise 2. Let's go to the next. Before continuing with the exercises, let's discuss now some probability propositions. Note that since E and the complement of E are always mutually exclusive events, and since the union between E and the complement of E is the sample space, we have that the intersection between E and the complement of E is the empty set, and the union of E with the complement of E is the sample space. Consequently, proposition number 1, the probability of the complement of E is equal to 1 minus the probability of E. Proposition 1 states that the probability of an event not occurring is 1 minus the probability of it occurring. Proposition number 2, if A is contained in F, then the probability of E is less than or equal to the probability of F. Proposition 2 states that if the event E is contained in event F, then the probability of E is no greater than the probability of F. It tells us, for instance, that the probability of a six-sided die landing with number 1 facing up is less than or equal to the probability of obtaining an odd number. Okay? Proposition number 3, the probability of the union between events 1 and 2 is equal to the probability of event 1 plus the probability of event 2 minus the probability of the intersection between events 1 and 2. Proposition 3 provides the relationship between the probability of the union of two events expressed in terms of the individual probabilities and the probability of the intersection of the events. That is, the probability of the union of two events is equal to the probability of event 1 plus the probability of event 2 minus the probability of the intersection of events 1 and 2. Now let's go to exercise 3. Let's discuss Sarah's holiday vacation. Sarah purchased 2 books to accompany her during her holiday vacation. If the probability of her liking book 1 is 0.5, the probability of her liking book 2 is 0.4, and the probability of her liking both books is 0.3, what is the probability that she will like neither book? What do we want? We want to have an estimate of the probability of her liking neither book, okay? But before doing that, and using propositions 1 and 3, let's find the probability that she likes at least one of the books. The probability of her liking at least one of the books is the probability of the union between liking book 1 and book 2, which is equal to the probability of her liking book 1 plus the probability of her liking book 2 minus the probability of her liking both books. Saying again, the probability of her liking at least one book, which is the union of her liking book 1 and book 2, is numerically equal to the probability of her liking book 1 plus the probability of her liking book 2 minus the probability of her liking both books, okay? The union represents at least one book, okay? Either one of them. And the intersection means that she likes both at the same time, okay? And using the values given by the exercise, we find that the probability of her liking book 1 is 0.5, the probability of her liking book 2 is 0.4, and the probability of her liking both books is 0.3, and this is 0.6 or 60%. This is the probability of her liking at least one of these 2 books. And since the event of Sarah liking neither book is the complement of the event of her liking at least one of them, we obtain that the probability of Sarah liking neither book, okay, we are going to represent this in this way, the intersection of her liking neither of them, okay, because the probability of her liking book 1 is P of B1, okay, the complement of this is not liking book 1, okay, so this is the probability of her liking book 1, and the complement is of not liking book 1, okay, and the intersection of her not liking book 1 and not liking book 2 is what we want. We want the probability of her liking neither book, okay, and this is this is equal to the probability of B1 union B2, the complement of it, okay? See that this is the complement of this, okay? This is her liking at least one of the books, and this is when she does not like any one of them, okay? And this is equal to 1 minus the probability of the union that we just calculated, okay? and it is 1 minus 0.6, which is 0.4, or if you prefer, 40%. Okay, my friends, this is the probability of her liking neither of n, which is the complement, okay, the complement of her liking at least one of the books. And this is all for exercise 3. Let's go to exercise 4. Exercise number 4. If two dice are rolled, what is the probability that the sum of the upturned faces will be equal to 7? That's the question, my friends. Let's go to the solution. We shall solve this problem under the assumption that all of the 36 possible outcomes are equally likely. That is, our sample space consists of, we have two dice. One position for one and one position for the other. Our sample space will consist of 6 times 6, 36 possibilities of numbers for, or of pairs for the outcome of rolling the two dice. One dice can land facing one up and the other 5. Okay, this would be one outcome, and after doing it many times, we may find 6 and 3 here. So we have 36 possibilities, 36 pairs of the result of die 1 and die 2. Okay? And from these 36, 6 possibilities are for the first die and 6 possibilities for the second die. Since we want the outcomes to add up to 7, the event of interest is, the event of interest, we need to know, before calculating the probability, we need to know the sample space, okay? The sample space will be 36 pairs, okay? 6 for the first die and 6 for the second, and we have 36 pairs, and the event of interest is the outcomes to add up to 7, okay? Then we have pair 1, 6, pair 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Okay? This is the event of interest. And if you count, you're going to have 6 here. 1, 2, 3, 4, 5, and 6. 6 pairs. Therefore, the desired probability is, the probability of event E is equal to 6 possibilities out of 36 possibilities that make up our sample space. And this is 1 over 6, which is approximately equal to 16.7%. Okay? And this is all for exercise 4. Let's go to exercise 5. Exercise number 5. If 3 balls are randomly drawn from a ball containing 6 white balls and 5 black balls, what is the probability that one of the balls is white and the other 2 are black? That's the question, my friends. let's go to the solution. Knowing that the ball has 3 balls, if we regard the order in which the balls are selected as relevant, then the sample space will consist of, we have 6 white balls and 5 black balls. And adding them, we have, regardless of color, we have 11 balls. Okay? And if we regard the order in which the balls are selected, that is, without repetition, we draw one and don't replace it. We're gonna have, and we want to draw randomly 3 balls, okay? We want to draw 3 balls. For the first position, okay? For the first drawing, we have 11 possibilities. And if we already removed one of the balls, then for the second experiment of drawing the balls, we're gonna have 10 possibilities. And for the third, we're gonna have 9 possibilities. And if we multiply them, we have then 990 possible outcomes. That is, we're gonna have 990 triplets, okay? Not pairs, triplets of A, B, and C, okay? This is a triplet. We're gonna have 990 triplets, which is the same as regarding each of the ball as unique, okay? We are regarding each of the balls as unique. Furthermore, since there are 6 white balls and 5 black balls, there will be, okay, we're gonna have here, we want to draw here in this first position 1 white ball and the other 2 black balls. This is the condition of the exercise. That is the question. What is the probability that one of the balls is white and the other are 2? Okay, let's separate this position here for the white ball, and let's separate these 2 positions here for the black balls. Okay, if you want to draw 1 white ball, then we're gonna have here 6 possibilities for white balls. Okay, because we begin with 6 white balls. And here for the black ball, we have here 5 possibilities for black balls. And if we already removed one of the black balls, when we draw it again, we're gonna have only 4 possibilities for the next black ball. Okay? And then we have, multiplying then, 120 outcomes in which the first selected ball is white and the other 2 are black. Okay? We are calculating the probability, but before we need to understand this problem of counting, okay? This problem of combinatorics. Likewise, there will be Now let's understand this. Okay? We want here to be black, here to be white, and here to be black. If we want to draw the first ball as a black ball, we want our first drawn ball to be black. Then we're gonna have, we begin with 5 black balls. We're gonna have 5 possibilities for the first removal. We're gonna have, for the white ball, we have 6 possibilities. We're gonna have 6 possibilities for the white ball. And as we have already drawn one black ball, we are not gonna have 5 possibilities anymore. We're gonna have 4 possibilities for the second black ball, and this multiplies to 120. Okay, we're gonna have 120 outcomes in which the first ball is black, the second ball is white, and the third ball is black. And finally, we're gonna have also this. The first ball, I wish it to be black. The second ball, I wish it to be black too. And the third ball, I wish it to be white. For the first drawing, I'm gonna have 5 possibilities for black balls, but as we already removed one black ball, we're gonna have now 4 possibilities for black balls. But we do not want any more black balls. We want the third ball to be white. And since we have 6 white balls in the ball, then we're gonna have here 6 possibilities of white balls. And multiplying, we have again 120 outcomes in which the first 2 balls are black and the third ball is white. Hence, okay, this is here the event of interest, my friends, and this is the sample space. And the probability that we wish to calculate is the probability of the event of interest. Alright? The probability of the event of interest is, hence, assuming that the randomly drawn means that each outcome in the sample space is equally likely, we observe that the desired probability is, the desired probability, okay, the probability of this event is equal to 120 plus 120 plus 120 divided by 990. Then the probability of this event occurring is 4 over 11, which is equal to 36.4%. Okay, my friends, this is exercise 5. Let's continue with the exercises, my friend. Let's go to exercise number 6. A committee of 5 is to be selected from a group of 6 men and 9 women. If the selection is made randomly, what is the probability that the committee will consist of 3 men and 2 women? Okay, my friends, this is the exercise. Let's go to the solution. But before calculating, let's observe a detail of this exercise. The committee has to have 5 people selected from 6 men and 9 women. And we are not imposing that the committee will consist of 3 men and 2 women. We are assessing, okay, we are estimating the probability that this event will occur, okay? So our objective is to calculate the probability that the committee will have 3 men and 2 women. Okay, my friends, this is the exercise. And first of all, let's understand our sample space. Okay? Observe that the probability of event E is equal to the number of elements of the event of interest divided by the number of elements of the entire sample space. So we need to understand our sample space. Let's understand our sample space. If the selection is random, regardless of gender, and with no replacement, meaning that no one can occupy more than one position at a time in the committee, okay? Only one person can occupy only one position, all right? The same person cannot occupy 2 positions. This is basic, all right, to understanding the problem. Each of the combinations of 15, we have here 15 people, okay, 15 people. And the committee has to have 5 people, all right? If we are not caring much about the gender of the people, okay, we are randomly selecting people regardless of gender. We don't care much about whether it is a man or it is a woman. Then we are gonna have 15 possibilities to fill 5 positions, okay? And we have 5 positions. This is going to be equal to this. We have 5 positions. We have 5 positions. And we begin with 15 people. 6 men plus 9 women. We have 15 people. But as every one of the members can only fill 1 position, then for the second position we're gonna have only 14 possibilities, all right? And as we have already selected 2 people here, for the third position we're gonna have 13 possibilities, and for the other position 12, and for the last position 11 possibilities, okay? And this is equal to 15 factorial divided by 15 minus 5 factorial. And what does it mean? It means that we have, when you see this 15 factorial divided by 15 minus 5 factorial, it means that we have 15 possibilities to fill 5 positions, okay? And this is equal to n factorial divided by n minus k factorial, okay? Where n is the possibilities and k is the positions. But it is not yet equal here, okay? I'm gonna tell you why we have to discount for the repetitions, okay? And additionally, we have to remove the repetitions for A, B, C, D, E. Imagine that we have a committee and we have chosen A, B, C, D, and E, okay? These are the people among the 15, okay? 6 plus 9, 15. Among the 15, we selected A, B, C, D, and E. And since committee, observe that it is important, okay? This part is important. Observe that committee A, B, C, D, E is precisely equal to the committee C, A, B, D, E, okay? The same members, the same members. Here we chose A first, but here we chose C first. Alright? And in this way, there will be, okay? There will be 5 factorial committees composed of the same people. There will be 5 factorial committees composed of the same people. Alright? And in this way, we have to divide here, by the factorial of 5. Okay? To complete the formula, we have to divide this 15 factorial divided by 15 minus 5 factorial divided by 5 factorial, okay? This part here you understood. 15 factorial divided by 15 minus 5 factorial. What does it represent? Represents the factorial of 15, but we don't go all the way to the end of the factorial, multiplying 3, 2, 1. No. We stop here, okay? Because we don't have 15 positions for these 15 people. We have only 5 positions. That's why we stop here instead of going all the way to the end of the factorial. Alright? This part here is easy. And this part here, why we need to divide it by 5? We need to divide it by 5 because of the repetition of the same people. As we said, if we select A, B, C, D, and E, D, E, A, B, C will be the same committee, made up of the same people, but chosen in a different order, okay? And this comes as 1. We have 5 factorial committees made up of the same people. And this is equal to 1 because it is equal. It is the same committee. That's why we divide here by the factorial of 5. And this is equal to the combination of n elements taken 5 at a time, k at a time, okay? Now we are using letters to generalize k at a time, okay? This represents the now it is right, okay? It is this. We are taking n elements, it's the combination of n elements taken k at a time. And this is our sample space. Our sample space is equal here to 3003. Alright, my friends? And now let's understand the event. We have already understood the sample space. We need to understand the event of interest. We are not interested in the entire sample space. We are interested in the event of a committee consisting of 3 men and 2 women. Okay, as we wanted 3 men out of 6 and 2 women out of 9, and removing the repetitions, for example, we wanted 3 men. 3 men. We are going to take 3 men from these 6 possibilities. Observe that from these 3 men, men 1, men 2, and men 3 is equal to men 3, men 2, and men 1. Men 2, men 1, and men 3, okay? So there will be 3 factorial repetitions of the same man. of the same man, of the same group of men. Okay? Then we are going to take, we want 3 men. We are going to take 3 positions for the men. We are going to separate 3 positions for the men. We have 6 possibilities for the first position, 5 possibilities for the second position, and 4 possibilities for the third position. And this is equal to 6 factorial divided by 6 minus 3 factorial. Okay? This is easy to understand. We have 6 possibilities, but only 3 positions. That's why it is 6 minus 3 factorial. We don't let the factorial go all the way to 3 times 2 times 1, alright? Because we don't have 6 positions for the 6 people. We have only 3 positions for the 6 people, okay? And removing these repetitions here, we divide this by 3 factorial, and this is equal to 6 factorial divided by 3 factorial, and this number is the possibilities for men. And now let's explore the possibilities for women. We have 2 positions for women, okay? We have woman. We have 9 women here. 9 women. Imagine that I select woman 9. Imagine that I select the woman 9 and woman 4. Okay? Then woman 9 and woman 4 is equal to woman 4, woman 9. Alright? Then we have to discount for this repetition, which is simply the factorial of 2. We have 2 positions for women and 9 women in the group. For the first position, I have 9 possibilities, as 1 is already participating. For the second position, I have only 8 possibilities. And this multiplication is 9 factorial divided by 9 minus 2 factorial, okay? I don't have 9 positions for the 9 women. I have only 2 positions for the 9 women. Then instead of the factorial going all the way, I will stop at 7, okay? Because I have only 2 positions here. And then it is equal to this is equal to 9 factorial divided by 7 factorial, but we haven't yet discounted for the repetitions, and to compute the combination of 9 women taking 2 at a time, we do the following: 9 factorial divided by 7 factorial, 2 factorial, and this is the number of possibilities of 2 women occupying this committee. Okay, having understood this, we are going to move on to the probability. We want to calculate this probability here, the probability of the event of interest occurring. Okay, then the probability of this event, okay, of 3 men and 2 women, the committee consisting of 3 men and 2 women, is going to be the combination of 6 men taken 3 at a time times the combination of 9 women taken 2 at a time divided by the combination of 15 people. Okay, we have a group of 15 people, 6 plus 9, taken 5 at a time, because we have 5 positions for all the people. Okay, we have 5 positions for all the people, and we have 15 people. This is the sample space. We don't want to calculate the probability of the sample space. The probability of the sample space is by definition 1. We want the probability of this event here, and this is equal to 240 divided by 1001, which is approximately equal to 24%. Okay, my friends, and this is the solution of exercise 6, my friends. Exercise number 7. A urn contains 10 balls, from which 9 are white and 1 is black. If 4 of these balls are withdrawn, one at a time, without replacement, what is the probability that the black ball is chosen? Okay, this is the exercise. Let's go to the solution. We have, if 4 balls are withdrawn, okay, we have 4 positions here. 4 positions. We are not going to draw only 1 ball. We're going to draw 4 balls. We're going to draw 4 balls. And we want to calculate the probability that from these 4 balls that are selected, what is the probability that the black ball is chosen? That is, what is the probability that the black ball is among the 4 balls that are chosen? Okay, my friends, and firstly, as we did in exercise 6, in exercise 7, we are going to understand firstly our sample space. Remember that the probability of the event of interest is equal to the number of possibilities of the event divided by the number of possibilities of the sample space. Okay? And without distinguishing them from white or black, okay, regarding them just as balls, we have 10 balls, okay? We have 10 balls. The sample space is this. We are not setting any requirement. There is no constraint, okay? When understanding the sample space, we regard the balls as simply balls, okay? For the first selection, we have 10 possibilities, and the exercise said that there shall be no replacement, and if we are not replacing the balls, for the second possibility, we're gonna have only 9 balls. As we already withdrawn 2 balls, for the third selection we have only 8 possibilities, and for the last selection 7 possibilities. Okay, and this is equal to 10 factorial divided by 10 minus 4 factorial. Alright, why not simply 10 factorial? You may ask me or your teacher or a colleague, why not simply 10 factorial? Because 10 factorial is 10 times 9 times 8 times 3 times 2 times 1, okay? We don't go, let the factorial go all the way to the end. Why not? Because we don't have 10 positions. We don't have 10 positions available. We have only 4 positions here. Okay, then it is not going to be simply the factorial of 4. It is going to be the factorial of 4. It is not going to be simply the factorial of 10. It is going to be only 10 times 9 times 8 times 7. Okay, and this is similar to this. The factorial of 10 divided by the factorial of 6. Okay, my friends, this is the number that we are working with, not the entire factorial of 10. That being said and that being understood, we are going to now remove the repetitions, okay? This is with repetitions. We have to remove the repetitions of this, okay? Nevertheless, we need to discount for the repetitions. Observe that we are selecting 4 balls. Observe that ball A, ball B, ball C, and ball D make up the same group as the B, A, C, okay? And so on. So there will be 4 factorial permutations of the same balls, and this is what we call the repetition of the balls. We have to remove the repetitions, and if we remove the repetitions, then our sample space will be the combination of 10 balls taken 4 at a time, and this is equal to 10 factorial divided by 6 factorial 4 factorial, and I already calculated and I found 210. Thus the actual sample space is 210 possible selections of 4 balls from a group of 10. We are not distinguishing color here, we are treating them as simply balls. We are not distinguishing the 9 white and the 1 black. We are going to distinguish them now to understand our event. The event of interest. What was the event of interest? We are calculating the probability that among the 4 selected, the black ball is chosen. Okay? And we are going to have to use a technique here. The probability, this is the technique. The probability that the black ball is chosen is the complement of the probability of choosing only white balls. Okay? One more time. The probability that the black ball is chosen is the complement of the probability of choosing only white balls. That is, we have 4 positions here. Okay, we have 4 positions. We are selecting 4 balls. And what is the number of ways? The number of ways we are using counting techniques, combinatorics, to calculate probability. What is the number of ways that only white balls are selected? We have 9 probabilities, 9 possibilities for the first selection, 8 possibilities for the second selection, 7 possibilities for the third selection, and 6 possibilities for the fourth selection. Okay? If we select, if we take 1 white ball, we have 9 white balls. We begin with this. We begin with 9 white balls. If we select 1 white ball here, we're not gonna have for the second selection 9 white balls anymore. We're gonna have 8 balls. And as we already removed 2 balls for the third selection, we are not gonna have 9 or 8 anymore. We're gonna have 7, and for the last selection, we're gonna have 6 possibilities of choosing white balls. Okay? And this is equal to 9 factorial divided by 9 minus 4 factorial. And this is half of the problem. We have to remove the repetitions. Okay? There will be, as we did here, let's say that we choose white ball 3, white ball 2, white ball 9, and white ball 6. Okay, and it is the same of white ball 6, white ball 3, white ball 9, and white ball 2. We're gonna have 1, 2, 3, 4, 4 factorial permutations of the same white balls. That's why we have to discount for these repetitions. Then the number of ways we can select only white balls is going to be the combination of 9 possible white balls taken 4 at a time. Okay? And this is 9 factorial, 6 factorial, 4 factorial. We are dividing by 4 to remove the repetitions. And consequently, the probability that only white balls are chosen is the probability of choosing only white balls. The probability of choosing only white balls is equal to probability only white is equal to this number here is 126, okay? It's gonna be 126 divided by the number of possibilities of the sample space, 210, which is equal to 0.6 or 60% if you prefer. But we have said that the probability of the event of interest, that at least that the black ball is chosen, is the complement of this. Then the probability of choosing the black ball is equal to the black is chosen is equal to 1 minus the probability of choosing only white, 0.6, and this is equal to 0.4, or if you prefer, 40%, my friends. And this is all of exercise 7. Okay? Let's go to exercise 8 now. Exercise number 8. A poker hand consists of 5 cards. If the cards have distinct consecutive values and are not of the same suit, we say that the hand is a straight. From a deck of 52 cards, what is the probability that one is dealt a straight? Okay, my friends, this is the exercise number 8. Let's go to the solution. Firstly, we need to understand what a straight is. If you are new to poker, you may not know what a straight is. We need to understand what a straight is. For instance, a hand consisting of the 5 of spades, 6 of spades, 7 of spades, 8 of spades, and a 9 of hearts is a straight. Okay? The exercise helped us with this. The exercise said that if the cards have distinct consecutive values and are not of the same suit, we say that the hand is a straight, okay? They can be of the same suit, provided that at least one of them is not of the same suit. The hand will be a straight of 5 cards. Now that we understood what a straight is, we are going to understand our sample space. The sample space is easy to understand if you understood exercises 6 and 7. it is going to be easy for you to understand the sample space. We have 52 cards in a deck, okay? We have 52 possibilities of cards in a deck. But a poker hand is comprised of only 5 cards. Then we have 1, 2, 3, 4, 5 possibilities because we have only 5 cards in a poker hand. Treating all the cards as equal, having equal probability, then if we select randomly a card from this deck of 52 cards, for the first selection you're gonna have 52 possibilities, okay? And as we have already removed 1 card, then for the second selection you're gonna have 51 possibilities, 50 for the third, 49 for the fourth, and 48 for the last selection, my friends. And this is equal to the factorial of 52 divided by 52 minus 1, 2, 3, 4, 5 minus 5 factorial, okay? We don't let the factorial go all the way to the end. We stop here because we don't have 52 positions for the 52 cards. We have only these 5 positions. That's why we divide this. We divide by 52 minus 5, okay? And this is the first part of understanding the sample space. Now we have to understand why we need to remove the repetitions. Let's suppose again that we selected cards A, B, C, D, and E, okay? If we are dealt a poker hand consisting of the cards A, B, C, D, and E, okay? It is the same of having the hand E, B, A, C, D, okay? It is the same. They are the same cards but in a different order, okay? And there will be 5 factorial repetitions of the same hand consisting of the same cards but dealt in a different order, but the order they are dealt is not important. What is important is the cards that you have in your hand, okay? There will be 5 factorial repetitions of the same cards, and we have to remove these repetitions. Then our sample space will be the combination of 52 cards taken 5 at a time, which is equal to the factorial of 52 divided by 47 factorial 5 factorial, okay? And this is a very big number, 2,598,960 possible hands, okay, my friends? All right, this is the sample space, or the sample space. And now let's understand the event of interest. The event of interest is to be dealt a straight in poker, remembering that if the cards have distinct and consecutive values and are not all, they can be, 4 of them can be of the same suit. But it is paramount that not all of the 5 cards are of the same suit to be called a straight, okay? This is the probability that we are assessing. And this is the second part of the problem. The first part is to understand the sample space. The second part is to understand the event. To determine the number of outcomes that are straight, let us first determine the number of possible outcomes for which an example of a straight happens regardless of suit. For example, the straight comprising of let's work with this example of straight. We have an ace, we have a 2, a 3, a 4, and a 5. Okay, this is a straight. An example of a straight. Okay, let's work with this example of straight. Since the ace can be any one of the 4 possible aces, alright, we have 4 suits in a deck, okay? If you are not accustomed to cards, okay, we have 4 suits in a deck. Then we're gonna have 4 different aces, one of each suit. Alright? Since the ace can be any one of the 4 possible aces, and similarly for the 2, for the 3, the 4, and the 5, there will be 4 twos of different suits, and so on. Okay, 4 fives of the 4 different suits. Then we're gonna have here for the ace, for the 2, for the 3, for the 4, and for the 5, we're gonna have 4 possibilities of aces. Okay, we have 4 suits. We're gonna have 4 possibilities for aces. We're gonna have 4 possibilities for 2s. We're gonna have 4 possibilities for 3s, 4 possibilities for 4s, and as we have 4 suits, we're gonna have 4 different 5s in this deck, okay? And if we multiply with 5, we find the 4 to the 5th hands with these cards, okay? 4 to the 5th hands with these cards, the ace, the 2, the 3, the 4, and the 5, bearing in mind that we have 4 suits, okay, and each of them we're gonna have 4 possibilities for the different suits. All right, there are 4 to the 5th, and this number is equal to 1024 possible outcomes leading to exactly 1 ace, 1 2, 1 3, 1 4, and 1 5. Okay, this is only one example of a straight. There are other possible straights, and we need to account for that. Nevertheless, since in 4 of these outcomes all the cards will be of the same suit, alright, this is a detail very difficult to spot. There is a detail here. There are 4 suits, okay? There are 4 suits. Let's take, for example, the hearts. The hearts is 1 suit. Among these 1024 possibilities of straights, there will be, for example, the ace of hearts, the 2 of hearts, the 3 of hearts, the 4 of hearts, and the 5 of hearts. And this is called a straight flush. it is not a simple straight, it is a straight flush. Then we have four different straight flushes when we have this rising values, okay, consecutive values, but when they are of the same suits, we don't have a straight, we have a straight flush, okay. And taking account of these four straight flushes, nevertheless, since in four of these outcomes all the cards will be of the same suit, a hand called a straight flush, it follows that there are removing the straight flushes, we're gonna have 4 to the fifth minus 4 equal to 1020 hands that make up a straight. Alright, so this is not what we're working with. We're working with this because we have to remove the situation in which the suit is the same for all cards, because it breaks with the definition of a straight. The exercise said that the definition of a straight is when the cards have distinct consecutive values but are not of the same suit. When they are of the same suit, we have four possibilities. When they are all of the same suit, it breaks with the definition of a straight. It is called a straight flush, not a straight, and we have to remove this. All right, and we have then 1020 hands that make up a straight of the form ace, 2, 3, 4, and 5. Okay? Similarly, there will be, so we have already discussed this. Now let's discuss other possibilities of straights. Similarly, there are 4 to the fifth minus 4 hands that make up a straight of the form 10, Jack, Queen, King, and Ace. Okay, this is a possible straight. Okay, provided that they are of distinct consecutive values, this can be considered a straight. Okay, so there will be again 1020 possibilities of hands. Okay, with a 10, a jack, a queen, a king, and an ace, and we have to remove 4 when they are all of the same suit. For example, if we have a 10 of spades, a jack of spades, a queen of spades, a king of spades, and an ace of spades, we don't have a straight. Okay, it is not a straight, it is a straight flush. Then we have to remove these 4 hands that are straight flushes. Okay, 1 for each of the 4 suits. And similarly, and now summarizing, because we have to take account of all the possible straights. Okay, you have understood this. Let's move on. For example, summarizing, for example, we have ace, 2, 3, 4, and 5, and we have 10, jack, queen, king, and ace. We're going to have here 10 possibilities of straight, okay, with different cards of different figures. okay, or numbers. When we vary only the number, we are not varying the suit. When we vary only the value of the card, we have 10 possibilities here. There are 10 possible traits of different figures, or if you prefer, different values. And 1000, as we said, 1020 traits using the same ranks. Okay, varying only the suit. This is called a value, or if you prefer, this is called a rank. The rank of the card. The suit is spades, hearts, and the value is called the rank. We have 10 possible traits of different ranks and 1020 traits using the same ranks. 10 of different ranks and 1020 of the same ranks. Okay, my friends, and ultimately the desired probability is going to be 10 times 1020 divided by the sample space. We calculated the sample space, okay? We calculated the sample space, and the sample space is this, okay? And this is equal to, all right, this is equal to this number here. This number, the multiplication of this divided by this, and it is equal to 0.0039, or if you prefer, 0.39%. My friends, this is the solution of exercise 8. Exercise number 9. Let's calculate the probability of a full house in poker. A 5-card poker hand is said to be a full house if it consists of 3 cards of the same denomination, varying only the suit, and 2 other cards of the same denomination, varying only the suit. And the denomination of these 2 other cards have to be different from the denomination of the 3 first cards. Okay? And the question, what is the probability that one is dealt a full house? Alright, my friends, this is the exercise. Let's go to the solution. But before calculating anything, we need to have a complete understanding of what a full house is. Firstly, we need to understand what a full house is. For instance, one kind of full house is 10 of hearts, 10 of spades, 10 of clubs, ace of diamonds, and ace of clubs. Observe that we have 3 cards of the same rank, 10 of hearts, 10 of spades, 10 of clubs, and 2 cards of the same rank, varying only the suit, ace of diamonds and ace of clubs. Okay, we have 3 tens and varying only the suit. We have 2 aces and vary only the suits. This is the definition of a full house. Alright, my friends, now that we know what a full house is, let's understand our sample space. Okay, let's understand firstly our sample space, because we want to calculate the probability of an event. What is the event? The event is to be dealt a full house. So the probability of the event of interest to be dealt a full house is equal to the number of elements of the event of interest divided by the number of elements of the sample space. We have to understand our sample space. Okay, we are going to compute the probability as the number of outcomes of the event of interest divided by the number of outcomes of the sample space. Our sample space is composed of all possible hands of 5 cards from a deck of 52 cards. Okay, that is, we have 1, 2, 3, 4, 5 cards. The poker hand is of 5 cards. And let's treat the cards equally, having equal probability from a deck of 52 cards. Without caring much about how they are dealt, we are only going to see the cards as cards, okay, without specifying them, alright? So if I draw randomly a card from the deck, for in the first selection, I'm gonna have 52 possibilities of cards because I have not yet selected any one of them. So there are 52 cards in the deck. As I already selected one, for the second selection, I'm gonna have 51 possibilities and so on. 50 for the third selection, 49 for the fourth, and 48 cards for the last selection. And this is equal to 52 factorial divided by how many positions do we have? 1, 2, 3, 4, 5 divided by 52 minus 5 factorial, okay? This is not yet the combination. We want the combination. This is not yet the combination. We have to remove the repetitions, okay? And remembering that we must remove the repetitions since the hands, observe that this hand here, A, B, C, D, and E, is precisely equal, exactly this. D, B, C, A, and E, okay? The cards were dealt in a different order, but once you've had the hand dealt to you, you're going to observe that you have precisely the same cards. Then there will be 5 factorial repetitions of the same cards. Alright, that's why we have to remove these repetitions. Then our sample space is going to be the combination of 52 cards taken 5 at a time, and this is equal to 52 factorial divided by 47 factorial 5 factorial, and this is a very big number, 2,598,960. Okay, this is our sample space. Did you guys understand why we removed the repetitions? Again, there will be 5 factorial permutations of the cards A, B, C, D, and E. Alright? In other words, this number is equal to 120. There are 120 possible hands with the same card. Thus, the actual sample space is the combination of 52 cards taken 5 at a time, which is this very big number there. Okay, 2,598,960 possible hands of 5 cards from a deck of 52 cards. Alright, this is the sample space. Now let's understand the event of interest. And what is the event of interest again? The event of interest is this: the probability of getting a full house in poker. Additionally, observe that there are different combinations of, for example, 2 10s. For example, imagine that I have here 3 positions. We understood that a full house is comprised of 3 cards of the same rank, varying the suit, and the other 2 cards of the same rank, varying only the suit. Let's suppose that this card here is a 10, this card here is a 10, and this card here is a 10. And let's suppose that this card here is a jack and this is a jack, okay? And how many 10s there are in a deck? We have 4 suits, okay? There will be 4 10s in a deck. Then the first selection of a 10, we have 4 possibilities. For the second 10 we have 3 possibilities, and for the third 10 we have 2 possibilities here. But we need to understand that again we're gonna have to remove the repetitions. Then this will ultimately become this, okay, the factorial of 4 suits for 3 cards, okay, and this is equal to, okay, let's only understand that this is a combination, alright, combination of 4 suits for 3 cards. Later we compute this number here, and the same for the jack. We have 4 suits for the selection of the first jack, but observe that the second jack must not be of the same suit of the first jack, okay? That's why we have numbers here in descending order, because they have to be 10s, but the second 10 must not be of the same suit of the first 10, obviously, because we have only 1 10 for each suit, okay? So if I choose a 4 of spades, obviously for the second position I'm not going to have a 10 of spades anymore. I'm going to have the other 3 10s and so on, okay? And here I'm going to have 4 and 3, and this, if I remove the repetitions, will be 4 suits for 2 cards, okay? This is what I wanted you to understand. Additionally, observe that there are the combination of 4 taken 2 at a time, different combinations of, for example, jacks, and 4, the combination of 4 taken 3 at a time, different combinations of 10s, okay? As the ranks have to be equal, the number, when I say rank, I say the number. As the ranks have to be equal, the cards being different only in the suit. Furthermore, there will be, observe again that we have 52 cards in a deck. Okay, we have 52 cards in a deck. And from this deck we have 4 suits. And what is the conclusion that we get? That we have 13 cards per suit. 13 cards per suit. Okay? and treating the pair and the triplet. When I say triplet, I say this. When I say pair, I say this. And treating the pair and the triplet as one, there are, okay, I'm gonna have here, we have 13 cards per suit. I'm gonna have 13 different cards to form the triplet, and as I already used one rank here, I'm gonna have 12 cards for the pair, okay? And multiplying then 13 times 12, which is 156 possible arrangements for the triplet and for the pair, okay? Since the ranks of the triplet have to be different than the ranks of the pair, it follows that the probability of a full house is, we are going to combine this with this, okay? Here I am varying only the suit. Here I'm varying the rank of the card, okay? I have 13 ranks or 13 values for the triplet, and as I already used one, I'm gonna have 12 ranks or values for the pair. But using the suits, not the ranks, using the suits, I'm gonna have a combination of 4 taking 3 at a time. For this rank, we used, for example, the 10, and for the pair we used the jack, okay? Combining this, we find 13 times 12 times 4, 2, 4, 3, okay? This is the number of elements of the event of interest, and we divide it by the sample space. And this is equal to 0.0014, which is equal to 0.14%. And this number is the probability that one is dealt a full house in poker, my friends. This is the number of elements of the sample space, and this is this, and we are calculating this probability here, okay? The probability of the event of interest, which is to be dealt a full house in poker. All right, my friends, this is all for exercise 9. Let's go to exercise 10. Let's go to the last exercise, my friends, and discuss the game of bridge. In the game of bridge, the entire deck of 52 cards is dealt out to 4 players. What is the probability that one of the players receives all 13 cards of spades? Okay, my friends, this is the exercise. Let's go to the solution. The first step will be to understand our sample space. Okay, observe that 52 cards. We have 52 cards in a deck. 52 cards dealt to 4 players is equal to 13 cards per player, okay? Each player will receive 13 cards in the game of bridge. The total number of ways to deal 13 cards to a player from a deck of 52 cards is given by the combination formula, okay? Is going to be the combination of 52 cards taken 13 at a time. Alright? and this is equal to 52 factorial divided by 39 factorial 13 factorial, and this is equal to 6.35 times 10 to the 11 possible hints, okay? An extremely large number. But let's understand this number. Where does it come from? Let's understand it. Observe that if we do not take into account the repetitions, we will be able to deal 13 cards to a player in such a manner, okay, where a player will receive 13 cards, 1, 2, 3, etc. until the last. Alright? 13 cards to each one of the players. Let's begin with John. John is participating in the game, and I need to give to him 13 cards, and from the group of 4 players I'm going to deal the cards to John first. Alright, let's forget the other 3. Let's deal the cards to John first. The first card that I am going to give to John, I'm going to select it from a deck of 52 cards, okay? As I already gave one card to John, for the second card I'm going to have 51 possibilities. For the third card I'm going to have 50 possibilities, okay? And as I am removing cards from the deck, for the last card there will be only 40 cards in the deck, okay? I'm going to have 40 possibilities of cards to give the last card to John, okay? So this represents 13 cards randomly drawn from a deck, okay? And this is equal to 52 factorial divided by 52 minus 13 factorial, okay? And remember that we don't let the factorial go all the way, alright? We are not dealing cards to only one person. I'm not going to give the 52 cards only to John. I'm going to give only 13 cards to John, because the other 3 players will need to receive other cards, their share, alright? 13 cards for each. That's why we stop here at 40 and don't let the factorial go all the way. If there was only John playing, I will let the factorial go all the way to the end. 3, 2, 1, alright? However, there will be 13 factorial repetitions of the same hand of 13 cards, such as, imagine that I have here card A, B, C, D, etc. until the end, L, M, N, okay? 13 cards. This will be precisely equal to the hand G, F, H, I, C, B, A, okay? Let's take the letters of the alphabet. From A to N, there will be 13 letters, and we are using the letters to represent in a generalized way the cards of the deck, these 13 cards. So I'm going to have 13 factorial repetitions of the same hand with the same cards, but dealt in a different order. Here, card A was dealt first, card B was dealt second, card C was dealt third. But it is possible that card G can be dealt first, card F can be dealt second, card H can be dealt third, okay? And there will be 13 factorial repetitions of the same hand with the same cards, okay? Meaning that although these hands have the same cards, the sequence in which they were dealt is different. That's why to complete the combination we have to divide by 13, the factorial of 13. Okay? This is our sample space. We have already understood the sample space. We have to understand the event of interest. There is only one possible way of dealing all the 13 cards of spades. Among all the possibilities, there is only one way of dealing all the 13 cards of spades, okay? So, what is the probability of interest? The probability that, for example, John is one of the players. The probability that John receives all cards of spades is equal to 1, because there is only one possible way of dealing all the cards of spades, divided by the sample space, divided by 6.35 times 10 to the 11th. However, there is a catch here, a detail that maybe you may not spot it, but as I thought about it, I reasoned about the solution. We have 4 players. We don't have only John playing. We have 4 players. Then this increases the possibility by a factor of 4. Okay, so the probability that the 4 players receive all 13 cards of spades is equal to 4 divided by 6.35 times 10 to the 11, and this is approximately equal to 6.3 times 10 to the negative 12. The probability, this number, 6.3 times 10 to the negative 12. This is the probability that one of the players is dealt all 13 cards of spades, my friends. And this is all for this video covering the topic of probability. I hope you liked the video and learned from it. I am a teacher, guys. If you want to have a conversation, discuss anything, or book a lesson, use my WhatsApp number, guys. Goodbye!